Okay, so this is a continuation. Now we are still going to analyze when x is equal to 2.4 meters. And now where we're going to test is we're going to test over there. Okay, so what we are trying to do now is stress, normal stress Z maximum when x is equal to 2.4. So this will be equal to minus m, moment is the same, right? And then we just want to divide by 308 times 10 to the power minus 6, because this value over here, right, you realize that the 308 times 10 minus 6 is acquired from here, right? So you just need to moment divided by ice, you get your stress max. So from here we found that the maximum normal stress with just bending moment is equal to 155.844. Times 10 to the power 6 Pascal. Okay. So we realize that this is less than 160, so the material is still able to withstand the load. And the next point that we want to check now we cleared 2.4. We want to check at 3.2, x equal to 3.2. Okay, so check where x is equal to 3.2 meters, right? So at 3.2, by looking at our shear force, get minus 40,000, bending moment is 32,000. So we know that V is equal to 40,000 Newton, and the moment is at 32 times 10 to the power 3 Newton meter. So this is what we know. Okay, so we're going to find shear. Okay, we're going to find shear, and they are like what we wrote earlier, YZ direction is going to shear YZ. So the area that we are concerned is the top part, the flange, right? So we are interested in the flange region, but the thickness, we're going to use this thickness over here. Okay, thickness. So we just need to find the flange, right? We just need to find this area over here. All right. So A. So this is equal to Q or V, Y direction, IXX, QXX divided by thickness. So we know that Vy is equal to 40 times 10 to the power 3 Newton. IXX, we know that it is equal to, what was the XX? So IXX is equal to, we got that value earlier, which is equal to 40 times 10 to the power minus 6. Thickness, we're going to go over here, we're going to look for the thickness of the web. So thickness 635 millimeters, so 6.35 times 10 to the power minus 3 meters. And then Q is equal to A Y bar, and the width that we know, the width of this material is 0.102 from the table. So the width 0.102, thickness is 0.01 meters, and then all you need to do is to get the centroid So center is D divided by 2. So 259 divided by 2 by 259, 0.259 divided by 2 minus by the thickness, okay, so minus by the thickness, which we get, which is equal to minus by 0.01. So the thickness is 0.01, okay, divided by 2. Alright, so this is 0.01 by 2. Sorry, I was not paying attention about something. So 0.259 divided by 2 minus by 0.01 divided by 2 times by 0.01 times by 0.102 is equal to 126.99 times 10 to the power minus 6 meter to the cube. Okay, so I just want to be sure, 0.259 divided by 2 minus by 0.01 divided by 2 times by 0.01 times by 0.102, 126.99. So from here we're going to find our shear XY, shear YZ. So the V is 40 times 10 to the power 3. The Q times 10 to the power minus 6. Then you have I, and the thickness, okay, so you take the higher thickness, okay, the smaller thickness, 126.99 power minus 6 divided by 40 power minus 6 divided by 6.35 power minus 3. So we got 19.998, positive 19.998 times 10 to the power 6 Pascal for normal stress. Then we calculate our bending stress, where X is equal to, so this is our location 3.2. So we're going to calculate at the intersection. Okay, we're going to calculate. So what we have now is we are calculating the stresses down here, okay, where the element is. So I'm going to draw my element. Okay, so this is where our element is. So moment, again, we know the moment is equal to 32,000. Okay, and we can put minus top or bottom, it's going to be the same. The Y, so the Y is the same like what we had before, 0.259 divided by 2 minus by 0.01 and then divide by I, which is equal to 40. So over here now, the 32 power 3 divided by, so 0.259 divided by 2 minus 0.01 times by 32 power 3 divided by 40 power minus 6. So we get 95.6. So minus 95.6 times 10 to the power 6 Pascal. Okay. So now we have a normal stress and now we have shear stress. So how does this actually look like now on a cube? Okay, so we draw the cube out. Okay, so we draw the cube out. So remember, we call this our x. No, this is our z. Y, and this direction can be x, or coming up can be x. So I want to check what they are. Yeah, it's x. So we know that over here you have compression of minus 95.6 times 10 power 6. You have a shear. So now the shear is going down. So I drew it wrongly there. So the shear is going down this way. So the shear y z equal to shear zy. This will be equal to 19.998. Okay, too crowded. The shear yz is equal to shear zy is equal to 19.998 times 10 to the power 6 Pascal. So looking at the direction is negative shear. Okay, it's negative shear. So next we are going to combine, right? We're going to combine the normal stress and shearing stress to acquire or to calculate the principal stress using Mohr circle. Okay, so the next video will show that.